In the last video, we saw spectral decomposition, which told us that any normal matrix has an orthonormal basis of eigenvectors. In other words, it looks diagonal when viewed in the basis of eigenvectors. There are many important implications of spectral decomposition. It is very helpful. Let's see some of the places where spectral decomposition is helpful. The first thing we will see is called operator functions. We know many functions on operators already. You can define m plus m, you can define m square, and so on. Someone might ask, can you define this? Can you define this? And so on. At least for normal matrices, spectral decomposition gives a very easy way to define these functions on operators. If a normal operator is written like this, it has spectral decomposition, we know that we will define f of m, a function on m, just by taking the function of its eigenvalues. The eigenvectors remain same. Remember, eigenvectors remain same and apply function on eigenvalues. This is how we are defining f of n. You can easily verify that it conforms with the definition of 2m m square. In other words, the eigenvalues of 2m are twice the eigenvalues of m. The eigenvalues of m square are square of the eigenvalues of m. So it exactly matches with the definition when we apply these simple functions. And this allows us to talk about root m, e to the power m, etc., etc. You can try taking some operators and apply functions on them and see how you define it. These operator functions will be helpful later. One of the operator function is known as trace. You might have heard of it. It is defined as sum of the diagonal entries of the matrix. At this point, this is a function on matrices and not on linear operators, because this definition depends upon the representation. It is not clear that if I look at a different representation or at a different basis, trace would remain the same. We will once again take help of spectral decomposition. First, look at the trace of a matrix UV. As an exercise, as a very easy exercise, you can show that this is the inner product between U and V. Another simple exercise would show that trace of AB is equal to trace of BA. In some sense, second implies 1. Once you have verified these, then given M as lambda I xi xi, taking the trace of M and noticing that it is linear, I will get trace of M is equal to summation lambda I trace of xi xi, and all these are going to be 1. So I get a definition in terms of eigenvalues. This is a basis independent definition of trace. It is easy to see that this is basis independent in the sense that if you change the basis, eigenvalues do not change. We have seen that M and P inverse MP have the same eigenvalues. The P was a basis change matrix. So here also, when you change the basis, the eigenvalues won't change. Hence, the summation I lambda I will not change. implying we have a basis independent definition of trace that is very, very useful. It's helpful always to think of matrices as linear operators and think of usual functions which you have thought of now as functions on the linear operator. From now on, your definition of trace should be the sum of its eigenvalues. Spectral decomposition will also be helpful in defining subclasses of normal matrices, which are going to be helpful in quantum computing. Remember, spectral theorem says that normal matrices have n eigenvalues and an orthonormal basis. These n eigenvalues need not be distinct, and then there is an orthonormal basis. It is easy to show that if you have any n complex numbers, again, that is because you can write the spectral decomposition. If you have n complex numbers and an orthonormal basis, the corresponding matrix will turn out to be normal. We get the subclasses by restricting these eigenvalues. In the case of normal matrix, any complex numbers are allowed. When we restrict these complex numbers to be of a certain kind, we get these subclasses. Let's look at the two important ones. First one is called Hermitian matrix. There are many ways to define it. This is the complex analog of a symmetric matrix. The usual definition given is that m star is equal to m. That means when you take that joint, it turns out to be same, or mxy is equal to m star yx. These are called Hermitian matrices, but the equivalent definition is that it's a normal matrix such that all eigenvalues are real. These two might look very different, but again, we will see the power of spectral decomposition. We know that m is summation lambda I xi xi. This implies that m star is summation lambda I star xi xi. This tells us that m is equal to m star if and only if lambda I is equal to lambda I star, implying lambda i's are real. Spectral decomposition gives a very short proof that these two things are equivalent. Notice that m star equal to m implies m is normal. Hermitian matrices are important because quantum mechanics uses eigenvalues to capture physical properties of quantum systems. Now, if you think about it, the physical properties should be real numbers. This implies that, or this shows that Hermitian matrices are going to be important for us. Whenever we want eigenvalues to be real, then we would get Hermitian matrices. This is one way to convince yourself that these matrices are going to be important. Let us look at a few of their properties. You can show them easily that for any B, not necessarily a Hermitian matrix, for all B, B plus B star and B star B are Hermitian. This is a standard trick to convert a non-Hermitian matrix into a Hermitian matrix. On the other hand, if A and B are two Hermitian matrices this time, they are known to be Hermitian, then A plus B is also Hermitian, though AB need not be. This is important. product of two Hermitian matrices need not be Hermitian. You can try to construct a counterexample. Take any two Hermitian matrices, their product will not be Hermitian with a very good chance. So you pick any two Hermitian matrices, you're very likely their product will not be Hermitian. Going to the second subclass, these are called unitary matrices. Again, you might have seen them before. These are analogous to orthogonal matrices in the real world. And the definition given is that M star M is equal to MM star is equal to identity. It is quite clear from here that unitary matrices are normal. Another equivalent definition, like Hermitian matrices, I can say that if that M is normal and all eigenvalues have amplitude 1. Absolute value 1. The equivalence proof, I will just say one word: spectral theorem. You have in a previous exercise calculated MM star. As soon as you calculate MM star and look at the spectral decomposition of identity, you will see that these two things are equivalent. Actually, for unitary matrices, there are many equivalent definitions. Let us see. This implies that M star is M inverse. That's almost equivalent. But this also shows that if I take two vectors u comma v and look at their inner product, this is going to be equal to mu mv. Reason being, this is equal to M star mu v, and notice that this is going to turn into identity. This tells us that unitary matrices preserve length as well as angles. This is very important because the inner product is preserved. That means length of any vector, angle between two vectors, they are all preserved by unitary matrices. This tells us that unitary matrices are basis change matrices. By applying unitary matrix, you are just looking at vectors in a different basis. They move orthonormal basis to another orthonormal basis. Under the action of u, you will get from an orthonormal basis to another orthonormal basis. We define A and B to be unitarily equivalent if A is equal to u dagger bu for a unitary u. This means we are looking at B in a different orthonormal basis. That's all. This is a very good intuition. If A and B are unitarily equivalent, then I am looking at B just in a different basis. A is B just in a different basis. What is that basis? That basis is going to be columns of U. This gives a very nice interpretation of spectral decomposition. If you remember, we said that spectral decomposition says that a normal matrix M is U star dl, and the columns of U were these vectors x1 to xn, which were orthonormal. This will imply, you can easily check, that U is unitary. So spectral decomposition says any normal matrix is unitarily equivalent to a diagonal matrix. And this is why normal matrices are so nice, because we like diagonal matrices. It's so easy to multiply diagonal matrices, add diagonal matrices, and spectral decomposition tells us if you look at the right basis, a normal matrix is diagonal. Whenever we have to handle a normal matrix, we generally go to that new basis where it is diagonal and then apply all the operators. Let me take an example of a unitary matrix. You can look at this matrix. This is going to be useful later. This is called Hadamard matrix. You can show directly by calculating that it is a unitary matrix. Calculate H dagger, calculate H dagger H, and you will show that that turns out to be identity. Another way to see that it is a unitary matrix is that if you notice, this matrix H takes 0 to 0 plus 1 by root 2 and 1 to 0 minus 1 by root 2. We call this state as plus and this state as minus. And you will notice that this also forms an orthonormal basis. Since H takes an orthonormal basis of 0, 1 to an orthonormal basis of plus minus, this implies H is unitary. I think we have learned all the basics required to define our second postulate. In the next video, we will see the second postulate, which will tell us what operators we can apply on a quantum system. Thank you.